Probably,
Okay, can you guys adjust it?
Yep.
Okay, and any chance you can scoot it a little closer, I'll pick up your sound. Okay. Alright, so you have open your lab binders to the page we were doing yesterday. I want you to look over your procedure. Okay, and then after you were done with your procedure, you should talk about why that happened. Ready, go.
So the question was, how does the atmosphere heat up? Well, we didn't really answer it, but
You just said talk about the procedure.
so what we did, our first step, we got the materials, the styrofoam cup, the vial. We didn't use the plastic cup. The first room temperature water, the hot water, and the thermometer.
Then step 2, we put room temp water in the styrofoam cup, in the vial, and then we fill the styrofoam cup with the hot water. Everything was all. And then we put
Oh, and then we put the cold water that was in the vial into the hot water. I think that was in the styrofoam cup.
Like we set the vial.
Yeah, I'll be right back.
The reason I think it's worked is because the styrofoam would contain the heat, so then the heat wouldn't escape, so that made the room temp water heat up.
And also, there was more hot water than cold water, and it was like surrounding the whole entire vial. Instead of having the heat source inside, it was surrounding it.
Yes, I said it worked because the warm water in the styrofoam cup warmed the water that was in the vial.
You guys have why it happened?
Yeah.
Okay, I'm gonna have you reset up the experiment and explain to the camera what you're doing.
Okay. We're going to remake the experiment and show the camera that we are redoing it.
Should we first get this temp?
No, we don't need that.
No, we don't need that temp.
We just need to place it in here. So this filled with
Wait,
hot water.
don't you need this temp first, just so you don't have to
So we're gonna take the temp of just the room temp water, which is, we have to give it a second. It's 22 degrees Celsius. Okay. Now we're gonna keep this in here, and now we're gonna set it into the warm water. And see if the heat rises. Or the temperature. Now you wait. Okay, you guys. That's really important. It's not even. So that was Georgia and Anna, I know. Now they're gonna explain what's happening here.
So the hot water that's in the styrofoam cup is making the water in the vial get warmer. Yeah.
It's already rose quite a bit. It's almost to 30, our stopping point.
I could never do YouTube. Oh, I know.
Okay, so we have.
Alright, now in addition, I have an extra challenge for you guys to keep track of. Make a T-chart on your paper. One side's going to have hot water temperature, and one side's going to have cold water temperature.
Okay, so it's got to 30.
Yep, go ahead and do this. So you make a T-chart. On one side you're going to have hot water temperature, And the other side you can have cold water temperature. Your first reading for the cold water temperature is 20. And your hot water temperature is going to be 60. Because that's what I'm reading here.
20 and 60.
And now, periodically, you're going to write down the temperatures with them both in.
So this one down.
Yeah, just leave it. All right, do we have things written down about what caused your temperature to increase? We got that down. Could people share what they have written down, please? Yes, ma'am.
The styrofoam cup held the
How many minutes are we
in
doing?
the hot water.
Should we do like 2?
Since the
Or more.
plastic in the
Hot water's
vial
cooling
allows
down.
Well, yeah, there's cold water in the middle.
the hot
There's
water,
gonna equalize.
kinetic energy was able to transfer into the room water than the water.
So through conduction, which is a vocab word we haven't even covered yet, it transfers heat from the hot water to the cold water inside the vial. Okay.
I had it was because the radiant energy from the hot water transferred to the room temperature water.
So radiant energy from the hot water transferred from the hot water into the cold water. Okay. Think about radiation and radiant energy. Energy that is radiated or transmitted through space in the form of rays, waves, or particles. So this is one way that energy travels, that energy is transmitted, right? But I don't know if I'd call that radiation because it's not rays. However, we get all of our energy from the sun, right? That is transferred from the sun to our earth to surfaces on the earth like water and soil and things like that.
Whereas the hot water,
All right. Someone else give me their writing. What did you write down?
yep, they both had a 9-degree change.
We put the vial in the cup of hot water, and but this happens because the vial was surrounded by the hot water, so it conducted the room temp water to increase in temperature. So it heated up.
Okay. So that use of the word conduction. Are we ready to just write that vocab word down? Let's talk about it because this is Brenda. You guys are on the right path. Here's your vocab word conduction. Transfer of energy from one place to another by contact. On this paper, on your loose leaf, underneath your thing. So transfer of energy from one place to another by contact. So we've got radiant energy traveling in waves. We've got conduction. What's the other type of heat transfer, energy transfer? Anybody remember? What's that? Yeah, convection. So those are 3 types of energy transfers that we've talked about. Now talk to me about kinetic energy. And the word temperature. And right up there, you guys either have temperature on page 24 or 19, if you could find that. Definition. Who's got that down? Yes, Anna?
Measure of kinetic energy.
So temperature is a measure of kinetic energy. Okay, so when we have an increasing temperature, what does that mean in terms of kinetic energy?
There's more.
It's a lot. It's more. It increases, right? So an increasing temperature just means more kinetic energy, right? And a decrease in temperature means less kinetic energy.
The hot water had a 7
How
or
does
8
kinetic
degree.
energy go away, or like how does it like be there? Like
It had an 8 degree.
Yeah, what happens to
Hot
it?
water has an 8
How is it
degree
there?
difference.
What is it?
Okay, so I want to go with this. Now let's just
36.
start a new loose leaf maybe, and we can carry on with that.
Never mind. 4 degree change. Whereas that had
This was left on a table yesterday, somewhere around there.
and cold had a 7 degree.
So the cold water is getting hotter, and the hot water is getting colder.
And they predict that they will
Okay, great.
equalize
So-
in temperature.
Ella, can you ask that again?
I said, like, where does the kinetic energy go when it lessens, or how does it, like, produce more? Or, like, how is it just, like, there?
Okay, so there's this law of physics that energy cannot be created or destroyed, right? And if we trace everything back to its very start of energy, where does all of our energy on Earth come from? The sun. Okay, right down to what we eat and how we burn energy, use energy. Okay, so it all comes from the sun. So the sun gets to Earth how? What's that transfer? Rays, radiant energy. Okay, so radiation comes through our atmosphere and it adds energy to particles in the form of what? And heat is what? Kinetic energy, right? So we have radiant energy transferred to kinetic energy. And kinetic energy does heat up air particles. So I've got this simulation for you, right? So this is energy transfer, and air particles are loose to bounce around, and they bounce off of each other, right? Collisions, they collide with each other. And since energy can't be created or destroyed, watch what happens at low speed to these two particles. We have a slow flying particle, and now we have a high flying particle. Bam! Watch it one more time. Slow flying particle, collision with a high flying particle. What happened to their speed, Georgia?
They both became the same. They equalized.
They both became the same speed, right? So what can you say in terms of kinetic energy? They transferred energy?
So the cold water was at 40.
Okay, so they transferred, so the faster one transferred some of its energy to the slower one, Ella?
So, like, does it reach equilibrium?
Sort of. It's not like convection, where they're moving
40.
away from
And
each
they
other,
both
where
had
they're
4
changing
degree
positions.
change.
But by colliding, they are transferring energy, and they'll get, yeah, yeah, like one will give energy to the other, and it will even out, like equilibrium. All right, watch at medium speed. And again. And now high speed because it's fun.
Oh, that's cool.
Do they cross paths or do they bounce out?
They bounce off of each other. Yeah. So here they collide.
Oh.
And so they change directions. Okay, so that's collision. So we can have energy transfer of kinetic energy from kinetic energy to kinetic energy, and that motion is what we feel as heat. Now, let's talk about conduction. Conduction happens through all three states of matter. Gas, like you saw here, or a liquid, or solid. So, you know how I feel about being cold, right? All right, imagine that I put a block of ice in my hand. What's going to happen to the block of ice? Hopefully. Okay, it'll melt. All right, talk about what's happening to my hand. It's getting cold. Okay, now talk to me on a particle level about energy transfer. How about you talk in your group first?
What was it? 41 for the cold. Right? 41.
Talk loud enough that the camera can hear you guys.
So,
The cold water is at 41 degrees Celsius, which is a 1 degree change. Same for the hot water. It's at 42 degrees Celsius, and that's a 1 degree change.
That's cool. Can you talk about the ice example?
Okay.
Oh, they're like,
And Miss Red was just talking how if you put an ice cube in your hand, it would start to melt.
And
That
get your hand
and that
colder.
would make your hand colder, and then they would slowly. How did she say it?
It would even out.
And then they would start to even out because your hand would be getting cold and the ice would be getting warmer to where they'd meet in the middle.
So that's what's happening to the water.
And that's what's happening
All right,
with the
talk
water
to me about
here.
my hand. Do we have
They're almost
more
meeting.
people willing to answer than 2 people I've heard from a lot today? 3 people I've heard from. Okay, Avery, I haven't heard much from you today.
The heat from your palm is transferring to the ice.
Okay, but you're talking in terms of heat. What is heat?
The faster particles.
Okay, so the particles from my hand. So check out conduction. Are the particles from my hand making contact with the ice?
Yes.
I'm touching it, right? Just a block of ice. So the particles from my hand are touching the ice. So how are the particles on my hand moving compared to the particles on the ice? They're fast, right? And so what's happening with the energy, with the kinetic energy? Avery?
What was the question again?
I've got fast moving particles on my hand compared to the slower moving particles of the ice that's sitting on my hand. What happens to the kinetic energy?
It tries to get to the ice.
Yeah, it's transferred to the ice. And so the ice particles then begin to do what?
Yeah.
Which means they're moving,
Faster.
which means they have more kinetic energy. Is that making a connection for you? All right. Everybody kind of get that? So on a particle level, I'm transferring energy to that ice block. And because the particles are moving faster, that substance changes states from a solid to a liquid. Now check this one out. You guys remember convection, right? This is one energy transfer. If I'm showing stuff up here, your eyes need to be up here. I'll wait. Go ahead and face up here, please. All right, I turn on the heating coil, and then we can see convection in the water. These are particles moving together, right? Okay,
And
so
now both of them
the
have
particles in a
reached
fluid
equal, which is 40.
are rising up. Okay, because they're becoming less dense. The particles at the top are sinking because they're becoming more dense. You get this convection cycle. Now, hold on. Then we switch to conduction, a different type of energy transfer. Check out the movement of the metal particles versus the movement of the liquid particles. Yeah, so the kinetic energy of the particles here is faster. So I turn the heating coil on, and now watch the particles moving. What's happening to the kinetic energy? Yes, ma'am?
The kinetic energy is getting faster in the pan, so it's getting the water more kinetic energy.
Yeah, so it's transferring it, right? And our heat source is down here. So we have this, okay, and it heats up the air particles, and the air particles move faster against the metal, and the metal particles move faster against the particles of water. Yes, ma'am?
But in the picture up there, the metal particles aren't moving at all. So does the kinetic energy just pass through it?
Let me see if I can.
They're moving.
They're just packed together.
Yeah, they move more. There's another one where we can actually watch, but if I turn this off, they stop moving as much. And they don't move a lot, but they do move.
Okay, maybe I can.
Yeah, it's hard from your direction. So you got these metal particles, and they're really like tight together, and so they're just barely moving. But then you got the water particles. That energy is being transferred through it. Okay, so yes.
Couldn't the water move faster because it's a liquid and not a solid like the metal?
And it does. It does move faster anyway, but then it really gets going because of energy transfer. So how did heat transfer from the hot water to the cold water? Is it conduction? Is it particles touching particles and transferring? can you together as a group draw a diagram
On the whiteboard.
What if we already
on your paper?
So when to
You guys all set with that? Yeah, just leave it. We're going to talk about that in a second. So go ahead and draw the diagram. Draw a diagram that shows the answer to this. That shows conduction. Can you show me conduction with arrows
So
and vocab words?
you would have the two.
And then we'll talk about it together. Can you talk together about what you're drawing?
So then we have to draw we have the two cups. Here, somebody show me.
Conduction.
So
If we allowed the two liquids to meet, would they reach equilibrium? Yeah, and that would be through
That
conduction,
one,
right? 'Cause they
that's
could
the
flow
start
into
of
each
our
other.
diagram. Like that's what
The different
you need to
densities
have.
would even out. But we're keeping them separate.
So when you draw arrows.
So we're going to talk
We
about
need to draw
conduction.
arrows from the hot water getting into this cup.
Now the hot water is on the outside cup.
We need to draw it going to the plastic first.
Yeah.
It needs to go like,
And
or
now
the,
we're gonna have to draw arrows going toward the colder water because it's the heat's transferring.
The heat's going from
Through
the cup in the
kinetic energy.
middle into the cold water.
The heat's transferring to the smaller cup with the colder water, and it's heating it up.
Let's find the right spot. So do you have any pieces of paper?
It's just going straight through this. Because these particles are made give them more energy, which heats up the inside.
And then continue on your that. Oh my god. No, you need to draw that with arrows.
So this inner cup is like, is this what I should
That's
do?
great, yeah.
Okay, so this inner cup's like with the colder water, and the outer cup has the warmer water, and the heat is transferring through the cups and warming this water in the center that's colder, and that's creating, what's that called? And that is called like conduction.
Right. Something to do
Are you married? Sure.
If it's just open, it can
She's getting married.
But if it's continuous, that's something to do with the carbs in there that it will, like, I don't know. Yeah. All right, I'm going to try and put into words what you drew. So tell me what I should start with. Okay, McKenna?
Some sort of heat source.
Talk to me about this experiment.
Which one?
The water, in the red water.
Here's the wrong. We drew like that almost, but
Okay, so you drew like a real life example.
so we just have like the flame, like when you have a stove,
Okay.
and then a pan and some water. Like we drew arrows like where the heat was going, where it was transferring.
Okay. Yeah, here's a simulation of real world conduction too. Like you're saying you're conducting through metal, you're conducting through liquid, you're conducting through air. So this is saying we've got radiant energy coming into the air particles. The air particle molecules make contact with the water, the road, and the land, and they absorb the heat. So they absorb the heat from particles and from the radiant energy. Talk to me about how to set up a diagram for this experiment. Yes, ma'am?
I have a question about that.
Which one?
Like that diagram up there.
Can we save it?
Yeah.
Okay, hold on to that thought. I know Danny has a question too. Taylor?
Oh.
Anna?
We drew like the outer cup
Okay, so you got the outer cup. What'd you have in your outer cup?
We had the hot water.
So there would be your heat source. So we have hot water. Okay, talk to me about how the hot water is moving. What are the particles doing?
They're fast.
Okay, so we have fast movement. And someone else tell me about the kinetic energy for the hot water. Yep. Okay, so we have high kinetic energy. All right, now what should I do next? What should I draw or write next? Avery?
We have a vial of cold water.
Okay, so we have cold water. Okay, someone talk to me about how the particles are moving in the cold water. Emily?
Slower.
Slower. And someone else tell me about the kinetic energy in there.
Slow.
Is that what the rest of you were going to say?
Yeah.
Pause. Hold it. Low kinetic energy. All right, now what do I do next? Anna?
Wouldn't you, like the cup itself, it starts to heat up?
So you guys are, okay, this is what all the other classes did. Besides last class, they did like energy transfer. Yeah? Right? But, yes?
But you have the glass or the vial container in between.
Right. So we have the vial, right? All right, so we have an energy transfer by contact. We have these particles that are moving fast, they have a high kinetic energy, and they transfer into the vial. Then we have the vial's particles that start to move faster, and they transfer into the cold water. So it's like these hit these hit these hit these. And so you start to see these speed up. And so you transfer this moving fast to this moving slow. And now, Danny, what was the question you asked me?
I had multiple questions. That first one.
The one about, does the hot water cool down or does it stay hot?
Oh, I said it wouldn't cool down because would it cool down if you mix them together?
Okay.
Because it's not cooling down when you have the vial in between.
Okay, so it's not cooling down when you have the vial in between, but I want you to listen to this. I set them up with an experiment. Can you explain what you guys did? Go ahead.
So there was hot water in the styrofoam cup, and then there was cold water in the vial, and we put a thermometer in both, and then each temperature, the vial with the cold water started to rise in the temperature, the hot water started to cool down, and they met at 40.
And they met at 40. And what's the temperature now?
The hot water is at 45 or 35 degrees,
35.
whereas the cold water's at 37 degrees.
Won't they just go down to room temperature now, though?
And now they'll both go down to room temperature.
But how come they mixed up?
How come they mixed up?
They split.
How come they split? Okay.
How did this get hotter after there?
Well, isn't the hot water going into there?
But we're not changing water, right? Because there's this barrier in between them.
The hot water particles.
So this hot water has transferred its energy into the cold water. It's losing energy, right? Can we say that this losing energy will lower the temperature?
Yeah.
And when this gains this energy, it'll increase the temperature?
Yeah.
And then how do you explain both of them dropping?
It just starts to cool down.
Yeah, they just got to the peak point and then they just start going down to room temperature.
Okay, where is their energy going?
It's going so
They're
trying
going
to
into each other.
they're reaching equilibrium.
But why wouldn't they maintain at 41?
Because that's not what the room is like.
Okay, so where's that energy going? Ella!
Into the air?
Into the air, sure. Through conduction, right? The air particles above it is picking up its energy, picking up its heat. Yes, ma'am?
This question, like with the pot thing, is that why it takes so long for water to boil? Because it has to heat up the solids, and
Yeah.
it takes so much longer for them to start moving?
Yeah, so it's got to like conduct the heat through different things. Talk to me about styrofoam. Does styrofoam conduct? Yes, sir.
Yeah, it like holds the energy, or holds the heat in.
But it doesn't act like the vial, right? So it doesn't conduct, it doesn't pass it through. So it's not transferring the energy, right? there were a couple groups, I don't think in this class, that wanted to do the styrofoam of hot water and a styrofoam of cold water. And I'm like, I don't know how that's going to happen, because what happens when you put hot chocolate in a styrofoam cup? It stays hot, so that energy doesn't transfer out. The only way it has to transfer out is up. Could you please put your book away and pay attention? Thank you. Danny?
So how come in like with your heating a pot of water, it takes a long time, but with this it took seconds, and it just rose up really fast.
Yeah. Maybe the vial isn't that great of a barrier.
Like, wouldn't the styrofoam be a lot bigger barrier?
Yeah, it'd be a lot more of a barrier, wouldn't it? Yeah. Okay. So you have out of class practice. Oh, one more question.
Oh, my question about that was like for conduction, why then is like blacktop hotter than grass if it just shares energy?
Why is blacktop hotter than grass?
Yeah.
Okay,
Or,
do you have an answer or a question add on?
Oh, I have like what I think. Isn't it because it's black and it like absorbs the heat?
But it should share it though, right?
It is collecting more radiant energy and more visible light energy, more energy from the sun than other objects, because other objects will reflect the light away. In the next units we study, I think at the end of the year is when we do our waves and energy unit, you will learn what causes us to see colors. And so part of what causes us to see colors is that the visible light that's coming in and hitting like the table,
Like this color?
it absorbs all the stuff, all the colors we don't see, and it shoots back the color we do see.
So like if we were to see the rays, would you see like just like rays just coming at you because you could see?
And like white, like a white surface reflects all the visible light. So we see it as white because it's all the light coming at us. We have a white star, it shoots all the colors down, and they bounce back at us, and we see that as a white light.
Shadows?
You're blocking the rays. Yeah, but to answer your question about the blacktop, it's absorbing all of the energy. It's not reflecting any of it away. Yes, sir.
Is that why if it's like pitch black or whatever, you can't really see like white, or it looks just like everything?
Yeah, because colors that we see are just reflections of what's not absorbed, what energy is not absorbed.
So, if we were to have any rays, everything would just be white.
No.
So then how does that work?
Wouldn't everything be black?
No.
So then how does
There'd
that
be
work?
nothing reflected. If there was no light, there wouldn't be anything.
Like we wouldn't see anything.
Yeah.
So like,
it would all look like
Wait, what color would it be then?
No idea.
What is it?
You guys are way outside my
So,
wheelhouse.
like,
You can stop this.
then
This is why I love science.
what if there's
Some other day